Hey everybody, how you doing? It's Pierre Holsenbus. I wanted to take just a minute at the beginning of this to say thank you. Thank you for taking the time today to stop along the way and take a peek at what I'm working on. This is a result of a bunch of work that I've been doing over the last few months, actually, regarding integration with Claude and just working with other AIs and coming up with this model or methodology, a protocol, if you will. So you'll get to see that here. I hope you enjoy the kind of fun nature that we do on this, but the whole point of it is just to really give you a good understanding of a tool that might be able to be very helpful for you. With that said, take it away.
Imagine managing the most skilled factory worker on the planet. They build complex parts at lightning speed, but they have one catch. Every time they take a break, their memory is completely wiped. When they start their next shift, they have no idea what they were just building, or even where they are. Modern AI coding assistants operate exactly like that worker. In computer science, we call this statelessness. Every time you open a new chat window or switch to a different computer, the AI starts with absolute zero memory of your previous session. To compensate, you spend 5 to 15 minutes copying code, pasting it into a new window, and re-explaining the rules of your project. Just to get the AI back, go up to speed. Because the computer forgets, you are forced to become the message bus, a manual, fleshy data link, a Meat Puppet, running context back and forth between different machines. We build software to automate repetitive tasks. Relying on skilled human engineers to act as manual thumb drives defeats the entire purpose of automation. So, if we look at this from a system architecture level, how do we get isolated, memoryless computers to work together? We use a protocol. For anyone new to computer science, a protocol is an agreed upon set of rules for formatting and passing data. Think of it like a perfectly structured relay race, where the baton smoothly bypasses the human standing in the middle. Our entire global internet runs on protocols. Yet in our most advanced AI workflows, we haven't established one. The AI sessions cannot talk to each other, so the human is left to fill the gap. Fixing this doesn't require inventing a magical AI with infinite memory. We just need a standardized set of rules, so these isolated sessions can leave notes for each other when we log off. That brings us to the Meat Puppet Elimination Protocol, CTURI MEP, a text-based self-enforcing system that relies entirely on tools developers already use every day. The first component, the identity file. By placing a specific text document in the main project folder, we give the AI a set of instructions. When you start a session, the AI automatically finds this file, reads it, and learns exactly how it needs to behave for this specific project. The second component, the handoff file, a highly structured shift logbook, 3 sections, what just happened, what needs to be done next, and what to watch out for. The structure has one absolute unbreakable rule. New entries go at the top. The newest information is always the first thing the next session sees. The third component, the transport layer. We use Git, the standard version control system, to automatically push these text files from one machine and pull them down to another. The result is a persistent memory for the AI, no new servers, no complex databases, simple plain text files and standard Git commands. So to see how robust this structure is, then we can look at a real-world stress test, April 3rd. 2 different computers updated the handoff file at the exact same time. This created a version control traffic jam known as a merge conflict. In a typical workflow, a clash like this crashes the process, the system freezes, a human untangles the overlapping text. But because we strictly enforce the newest on top rule, the AI could read its own protocol. It looked at the conflicting dates, identified the chronological error, and knew exactly how to merge the timelines. It stacked the dates correctly, saved the fix, pushed the code, closed the session, and without a single human click. And applying a strict structure the AI can actually understand allows the machine to organize its own history. This provides the mathematical logic required for a stateless AI to reason through an error and fix its own operational failures. This logic scales further when we consider that engineers rarely use just one tool. one AI ecosystem for architecture, a second for formatting, a third for code. To pass context across different ecosystems, we use a simple conversation URL as the baton. You take a web link from your brainstorming session and paste it directly into your coding session. The receiving AI reads that link, extracts the key decisions automatically, and updates the shared project log. Now, every future session knows exactly what happened, regardless of which tool you used. A single convergence layer. Route each task to the AI model best suited for the job. Never pay the time tax of re-explaining the project history. The core engineering takeaway: highly scalable, reliable systems often run on simple rules and existing tools, not massive, complicated, new infrastructure. Adopt simple text protocols. Remove the friction of acting as a manual message bus. Let the context handoffs lock into place on their own. Stay focused on high-level logic. Check the link in the description. Explore the Nukasoft open source repository. Install the identity file into your own environment. Start experimenting today. As we build more advanced software, designing the invisible rules of communication is just as critical as writing the code itself. Let the computers handle the relay pass. Don't be a meat puppet.
Well, I hope that makes sense. Thank you so much for your time today, and let's just keep in touch. Thanks. Hello, test 1, 2.